If you are like me, you watch and read a wide variety of reports about climate. The consensus is that Arctic ice is melting, ocean levels are rising, ocean pH is changing and not getting better, and global temperatures are going up. Then I read reports that say the above is not true. Arctic ice is actually growing and at astounding rates. Ocean levels are not rising, and while the temperature has gone up, it's not significant. I look up reports that are cited from either side of the argument, and within minutes realize I do not have the appropriate knowledge to begin to understand what they mean. They are complex. They are extremely specific because science demands that the hypothesis focus on defined elements. The results of an individual experiment are just that and need to be taken in the context of the whole, which is challenging because the world we live in is extremely complicated. I have reached out to a wide variety of people who read the reports differently from one another. This week, I read in a Canadian newspaper that the World Meteorological Organization, a trusted source, says Canada had a very cold 2019. So I looked it up, but I couldn't find that statement. Instead, I read on the WMO site, 2019 concludes a decade of exceptional global heat and high impact weather. Where is the truth? In this conversation that matters, I talk online to Environment Canada climate scientist Greg Flatto about climate, and he clears up a number of issues for me. And because our conversation extended far beyond my broadcast window, I have broken this conversation into two parts. Here now is part number one.
Conversations That Matter is a partner program of the Centre for Dialogue at Simon Fraser University. The production of this program is made possible thanks to the following and viewers like you. Please become a patron at conversationsthatmatter.tv.
I have long wanted to have a conversation with somebody who actually is a climate scientist, but I don't know exactly how do you define what makes somebody a climate scientist? So what kinds of credentials and studies do you undertake to get that kind of official designation?
Well, there are a lot of people who are climate scientists who work in the field of climate research. Many of us have different backgrounds. I mean, it is, as you allude to, it's a little different than being a dentist or a lawyer. I mean, it's pretty clear what those things are. Most of us who do research in climate have a background either in physics or mathematics, in some cases more specialized areas like atmospheric physics, atmospheric chemistry, oceanography. In my particular case, my background is actually in engineering. My PhD is in engineering science or engineering physics. And the work that I did in my PhD was really numerical modeling, computer modeling. And that's a kind of a subset of mathematics and physics. And that's the sort of work that in the group that I work in, which is developing global climate models and using them to understand how the climate system operates and to make projections of how the climate system will change in the future under different emission scenarios. That's the kind of skill set that a lot of people in our group have. But we also have people with expertise in processes in the atmosphere, the way that clouds form, the way that radiative transfer in the atmosphere works, the way that the ocean circulation works, the way that terrestrial ecosystems work. There's a big range of expertise that you have to pull together in order to develop one of these comprehensive global Earth system models that can be used in this kind of science.
When you take a look at a changing climate in Canada, for instance, because of course you're with Environment Canada, this is going to be primarily where your focus is. What are some of the elements that you put into that calculation that help you understand what's happening?
In the report that we released, Canada's Changing Climate Report, there's a combination of both observational evidence and model-related evidence. The observational evidence makes use of all of the observing stations that we have in Canada and have had for a long time. Those observations are corrected in various ways when there are differences in the way that measurements are made and the location of those measurements and so on, to produce a homogeneous record. And from that homogeneous record, we can ask, how has the climate changed in Canada, in particular thinking of basic variables like temperature and precipitation? And how is that compared to the changes that we see elsewhere in the world? So this same kind of activity is done globally. This report was aimed at really focusing in on Canada. And what we see is that the increase in temperature over the historical period in Canada has been at roughly double the rate at which the global temperature has been increasing. And that's consistent with the increased rate of warming at most high latitude countries.
I got to get you to hang on for a second while we take a quick commercial break. We'll be right back. Conversations That Matter is brought to you by Odlum Brown, a client-focused investment firm that starts client relationships with straightforward conversations focused on you, your aspirations, and your investment priorities. Odlum Brown has been a supporter of Conversations That Matter from the day we started this show. Their only condition was that we provide a non-biased conversation with people from all sides of all sorts of issues. And of course, we couldn't produce this show without the support of Oh Boy Productions. If you're looking to produce a show like this one, I suggest you reach out to Oh Boy. They can help you produce it, and they can help you build your audience. And we also need your support. I ask you to please pledge $1 per show by going to conversationsthatmatter.tv/donate, because those dollars add up and play an important role in helping us produce this show. Now, back to the show. So I listened to some of the response or reaction to that, and I had a couple people point out to me that, well, you know, it's hard to measure that in Canada against the rest of the world because we're the second largest landmass in the world. Of course, we're going to see variations in that data. How do we answer that so that we say, no, this science is accurate?
We do have a very well-established observing network in Canada, and the observations that we use to make those conclusions are very robust. They follow the measurement instruments, the measuring approach, the methodology, the standards that are adhered to are laid down by the World Meteorological Organization. They ensure that everyone that's making weather and climate measurements is doing so in a consistent way so that they can all be put together. We approach that in the same way that the international community does. And in fact, some of the researchers in Environment and Climate Change Canada have been leading in some areas of how to address the inhomogeneities in the climate data record that arise from moving measurement stations and so on. So we have a very robust observational database. It is, of course, much more robust in southern Canada than it is in northern Canada because the observing network, as is the population, is much more sparse. And so we have fewer stations in Arctic Canada than we do in the southern part of Canada, but still enough to make good estimates of the averages from 1948 onward.
You're pretty confident that you've got a pretty clear picture of where we're at.
Yes.
Yeah. So can I go through with you a number of things that, you know, I've been trying to understand this over the years, and I get bits and pieces of information, and I'll admit that I'm like anybody else. I gather a certain piece of information, it consolidates in my brain, and I think, oh, okay, that's the answer. But I've never had the opportunity to actually speak to somebody like you and say, well, is that assumption correct? And that is that, you know, number one, I'd take a look at Canada, and I've been told that we have approximately 39 billion trees in Canada versus less than 39 million people, and that those trees sequester carbon. And there are some people who say, well, as a result, even with the amount of carbon that we're producing, we're actually not, like, we're consuming more carbon than we're producing. Is that true, or is it false?
It's false, and it's a misconception that arises from only thinking about half of the equation. So when you think about a tree, when a tree grows, it the process by which it grows is photosynthesis. And photosynthesis takes energy from the sun, it takes water from the ground, and it takes carbon dioxide from the atmosphere, and it turns that into plant material, cellulose and sugars and things. Now that's the incoming part of the calculation. It's taking carbon dioxide out of the atmosphere and growing a tree. But now when that tree dies, either it falls over and decomposes or it burns in a forest fire, all of that carbon that it took up goes back into the atmosphere. So when you look at a mature forest, a large area of mature forest, there's trees growing and there are trees dying at the same time. And on average, it's basically neutral. It's taking up as much carbon as it's giving back, because if it was only taking up carbon, that forest would keep getting bigger and bigger and bigger, and the trees would ultimately, become bigger and bigger. They don't. They reach a limit. The density of the forest reaches a limit, and at that limit, the forest is, on average, taking up as much carbon as it gives back. It's not quite in balance. It does take up a little bit more than it gives back, because some of the carbon, a small fraction, is stored in the soil and ultimately accumulates in the soil and in the vegetation on the forest floor. But it's the amount that a forest accumulates is the small difference between two very large numbers, which is the large number of how much a forest takes up and the large number of how much it gives back.
So why is it important that if and please correct me if I'm wrong about this, that if carbon isn't created or destroyed because it fits into that law of thermodynamics, why is it so important that we maintain that very delicate balance?
Sort of two avenues to talk about there. The first is the concentration of carbon dioxide in the atmosphere is effectively the determinant of the temperature change, or the change in that concentration in the atmosphere determines how the temperature in the atmosphere will change. So there's a natural greenhouse effect that's mainly driven by water vapor in the atmosphere, but there are other greenhouse gases like carbon dioxide, methane, nitrous oxide, a number of them that all have the same property. And maybe if you'll allow me just a momentary excursion here to just explain it, and then maybe that helps to explain why it's important. So that natural greenhouse operates by allowing sunlight, all of the energy that we have that runs the ecosystem, that runs the weather, that runs the ocean circulation, all of that energy ultimately comes from the sun. That the sun radiates energy down in what we call shortwave radiation. That's the visible light that we see. The atmosphere is relatively transparent to shortwave radiation. That radiation comes right through. That's why when you look at the sun, you feel it. The ground, the ocean, the lower parts of the atmosphere absorb some of that energy, and warm bodies emit long-wave radiation. So when long-wave radiation is the infrared light that you can't see, it's the heat that you feel from a campfire or a fireplace. That's the long-wave radiation. So anything that is at a temperature above absolute zero radiates heat away. So the Earth is radiating that heat back into space. The atmosphere is opaque to long-wave radiation. It's transparent to short-wave radiation, but opaque to long-wave radiation, because molecules like water, the water molecules, carbon dioxide molecules, other molecules in the atmosphere absorb that long-wave radiation. It excites them, and then they re-emit it. So a lot of that re-emitted radiation comes right back down to the surface, and that effect is what we call the greenhouse effect, and it keeps the surface of the planet relatively warm. If we didn't have that natural greenhouse gas effect, that natural greenhouse effect, the average temperature of the planet would be something like minus 18 degrees or something. And it's currently about plus 12. So there's a huge warming at the surface of the Earth that's due to the natural greenhouse effect. So now if you change that greenhouse effect, you change the temperature. And by putting carbon dioxide into the atmosphere, you change that greenhouse effect. You make it a little bit stronger. And there's subtleties about how carbon dioxide does that and how methane does that, even more powerfully, how other chemicals do that. The point is that as you add these extra greenhouse gases to the atmosphere, it makes that greenhouse effect stronger and makes the surface of the atmosphere warm. And that basic physics has been understood since the 1800s. The first papers published on this date back to the 1800s. It's well understood physics. Now, in terms of the carbon and where it is and how much of it can be released and so on, so it is a case, you're absolutely correct, that there is only a finite amount. We have a planet, there's not carbon coming in from space and it's not leaving to space, so there's only so much carbon. A lot of that is in rocks that is basically inert as far as we're concerned. But there is a lot of carbon stored in coal and oil and natural gas that are the residue of plants and animals that lived a very long time ago, and their decomposition products are now locked up in these hydrocarbons. That's basically solar energy that was stored millions of years ago by those plants and is now captured in there in the form of carbon that can be oxidized. So if we dig it out of the ground and oxidize it, it produces carbon dioxide. It adds to the concentration of carbon dioxide in the atmosphere and keeps tipping the balance towards a warmer and warmer surface climate. So it's not so much that there is a magic number. The pre-industrial value for the last 10,000 years or so since the last ice age has been roughly 280 parts per million. We're now at about 400, directly because of what we've put into the atmosphere. Doesn't necessarily mean that 280 is a magic number or that 316 is the optimal number or anything. The point is that the more carbon dioxide you put into the atmosphere, the warmer it will get. And the problem is that carbon dioxide, when you put it in the atmosphere, it has a very long lifetime. So if we were to just stop putting carbon dioxide into the atmosphere today, the temperature that we have already reached, which is about 1 degree above pre-industrial on a global average basis, would stay the same for many, many centuries.
I've had a conversation with somebody who is a physicist and says, well, yeah, that's true. You add more carbon into the atmosphere, you are going to see a warming effect. And in the increase from 280 parts per million to 400 parts per million, he agrees that the addition of extra carbon has contributed to an increase in temperature, which is, I think, over the last 20 some odd years, about 1 degree Celsius. Is that right?
Yes. Well, since about 1850, from 1850 to present, it's about 1 degree on a global average basis. About double that for Canada.
So he said that, okay, in that 1 degree difference between 280 to 400 parts per million, he now says because of a logarithmic formula, you wouldn't see that increase again until you got to 800 parts per million. And I'm trying to think, okay, well, how does that make sense? Is he misguided there?
No, it is a logarithmic relationship between concentration and radiative forcing. I mean, this is getting kind of into the weeds of the physics here. So if you look at the observational record, the concentration of carbon dioxide in the atmosphere has been going up basically exponentially. It's curving up and it's constantly accelerating. If you look at temperature, it's been increasing more linearly. And that's exactly the response that you get from these logarithmic relationships. An exponential increase in CO2 gives you a linear increase in temperature.
So I also talked to Freeman Dyson at the Institute for Advanced Studies in Princeton, New Jersey. And he said, well, it's the sun, and in particular radiation from the sun, because I recognize that the temperature of the sun doesn't change, but when we go into a period where there's a Maunder maximum and there is an increase in coronal mass eruptions and solar radiation that starts to fill our solar system, the explanation that was given to me was that the thermosphere then expands, and that this is having a warming effect as well, and there are suggestions, and the problem with trying to predict this, especially with the sun, is how do you know exactly what it's going through? That we're moving towards a Maunder minimum, and that there may be a reversing effect of that. Is that a correct assessment or a definition of what's happening in our relationship with the sun? And how it affects climate, of course.
Yeah, it's not it's not quite correct. So it is true that the sun does have an effect on climate, and it is true that the irradiance of the sun, that is the amount of radiation that we receive from the sun, changes over time, and changes in various ways. On very long time scales, the output of the sun changes because of the way that stars evolve. But that's a billion year kind of time scale. On a shorter time scale, there's an effect that has to do with the way that Earth orbits around the sun. So the Earth doesn't orbit in a circular way around the sun. It's an ellipse, but the shape of that ellipse changes over time. The angle at which our North Pole, our rotational axis is relative to the plane of the solar system, that changes. It wobbles a bit. So there's these different variations in our orbit. Those have time scales of 25 to 100,000 years, and those are clearly associated with the comings and goings of ice ages. And the reason that they cause the climate to go through warm and cold periods is because when the orbit changes, the timing and amount of solar radiation we receive from the sun varies. On shorter timescales, the timescales that we're talking about, historical climate change, the next century, that sort of thing, there's a very small secular trend that can be detected, but it is tiny. It can in no way explain the changes in temperature that we see. There is also this 11-year solar cycle, roughly speaking. It's not it's not like a metronome, but it does roughly an 11-year period. You go from these solar minima to solar maximum. It's hard to discern those in the climate record. If you carefully analyze it, you can see this small signal, but the amount that it's changing is a very tiny percentage of the average radiation that we get from the sun. And so it's very difficult to even detect that signal in the climate system. The Maunder minimum argument is that those periods of solar minimum and solar maximum get smaller, and we go into longer periods of solar minimum. The difference between an extended period of solar minimum and an extended period of solar maximum is, as I said, a very tiny percentage of the solar radiation that we get from the sun. And so the experiments that have been done with climate models and through other lines of evidence indicate that really is a very small impact on the climate system. We do, in the climate models that we use to simulate historical climate, include the observed changes in solar radiation, solar irradiance. We don't have available to us predictions of future variations in solar irradiance, but we do include sort of an ongoing cycle. But it's really a tiny term compared to things like land use change, to greenhouse gas emissions, to aerosol emissions, even to volcanic forcing, which has these episodic cooling events. All of those are much bigger than the solar forcing.
That was part one of a two-part conversation with Mr. Flatto. Part two will be published in 4 weeks from the airing of this episode.